Do you know why? Because you heard it's the best class at the college, right? They heard that it's just the best class. Anywhere you go, the anatomy and physiology. Who couldn't love studying about anatomy and physiology, especially human anatomy and physiology? No, seriously though, why are you in the class?
The building blocks.
Because what?
It's the building blocks.
Okay, so it's the foundation of the health professional that you will become. And that's really what I wanted. That's really what I wanted, because that's really the truth. Most people say because my advisor told me I had to have it, right? You know, and the best answer I've ever had was because my mama told me. And I have had that answer, and I loved it, because people should do what their mamas say most of the time. So, but honestly, I need you all to realize, I know you don't know me yet, and some of you do, and maybe since they're not running out of the room, you'll hang with me a little bit. But I say this in all sincerity, this is the foundational course that you need to, that will establish what type of professional you're going to become. This is not a crossing a T or dotting an I class. And you're not in here to just get your C or better and go on. You're in here to realize that this is maybe the beginning. For some of you, it's not. It's this is just more along the way. You're already EMT. Are there any EMTs in here? And do I have any LPNs? I have some LPNs. I have CNAs. So I have some of you who really have a good foundation right now. But this class, you do not want to just do it to get through it. You want to own it. And when people tell me that they're in a class and, I'm going to have to memorize so much stuff, and this is so hard. I've heard it's hard. I heard there's a lot that you have to learn. If you ever say you're going to memorize something in my class, that's really a bad word for me, because you haven't learned it. And unfortunately, what has happened for most of you, not all of you, but for most of you, our education system has let you down, because we've had this lecture-based education system. And for lectures, they don't really work. Now, that's nice of me to say when I'm standing up here lecturing at you, but they usually don't work. But here's what we do know. For you to learn, you have to be an active participant. You have to be engaged. You have to try to stay engaged as much as you can. Unfortunately, there's so much content in this that I feel responsible. I do need to give it to you. So a lot of this is lecture-based, but you have to do what you need to do to stay engaged. That's why on the syllabus you'll see there's no electronic devices allowed in here. I'll give you one warning for a phone, and then I will drop you. So phones need to be off. They need to just not be out ever, because you need to stay as engaged as you can. I need you taking longhand notes. Why? Because what we know is typing notes does not hit the same neuronal circuits as you do it taking longhand notes. It will be better for you in the long run. It's like saying, go get that switch. It's going to be good for you, Rafi. But actually, it's proven. We know that at a physiological level. So whatever you can do, because I get that in the first few minutes, you're just seeing if I'm going to be dangerous to you, because that's human nature. That's animal behavior. You have to be alert, or you could be wiped out, right? Once you figure out I'm not going to harm you in any way, you start thinking about things that are legitimate. Do you have enough gas to get home? Did you leave your child sick somewhere this morning? You knew they didn't feel well. Is that teacher going to treat your child right? Is that boyfriend, significant other, girlfriend, whoever it might be in your life, really thinking that you're going to put up with that? So anyway, you're thinking about a lot of things, and I get that, but you've got to try to stay as engaged as possible. I'll try to do as much as I can to give you what you need. We're going to be recording lectures. So this part, here it is. But we're going to be recording lectures every time we come in here. We hope the technology works for us. I will have those lectures up usually by late in the afternoon of the lecture day. They will be on Canvas. How many of you logged into Canvas? Hopefully you haven't had too many problems. It's brand new for us. For some of us who've had to go to Canvas this semester, it's brand new to the college. You will see underneath the syllabus, under modules, the syllabus, and begin here, you will see a module that says lecture recordings, and then you'll see dates. And so whatever date you might need to refer to, that's great. Those lecture recordings, some people will never have to go to them. But I have had students who say that once we start, it's really hard for them to take notes. So they sit and listen because they know they're audio learners, that helps them. And then they listen to the recording later where they can stop it and take longhand notes to do their work from. So that's how they do that. Now, that doesn't mean you'd ever have to listen to lecture recordings. If you miss, though, I would advise you to listen to the lecture recording. You'll see why in just a second when we go over the syllabus. How many of you actually printed off your syllabus or looked at it in Canvas? Raise your hands. I'd be proud of that because I'm so fortunate to be able to work with students who have had some classroom experience, what I call serious classroom experience. And so they kind of know to do that before they even come in, and that's great. Y'all are ahead of the game. But anyway, I'm sorry, I forgot what I was saying, but I want to let you all know something. I'm humbled to be a part of your journey, and I know that sounds so incredibly corny and cliche, and I get that, but I can't tell you, like, I get chill bumps sometimes thinking about what you all are about to do, and some of you are already working in the fields. Y'all have chosen fields that you will never be able to be an expert in your field because so much is changing all the time. And the best medical professional is the medical professional who will say to their peers, but also certainly to their patients, you know, I'm not quite sure about what's going on here, but we're going to find out. The best primary care provider, if you close that door, the best primary care provider is the one who says to you, sees you as a whole person, isn't just treating you for what you came in to complain about, but is asking deep questions and saying, you know what, I've seen this before, but yours is not acting exactly the same. We need to do more. I might need to send you to a specialist. Right now, it's taking about 10 years to get the newest research, the newest data to the primary care providers. That's too much time, isn't it? That's too much time. You, as a medical professional, you can shorten that time by realizing that you have to be lifelong serious learners. Because what is written in your textbook, and some of you just paid an outrageous amount, and my apologies for that, but anyway, if it's printed, it's already old. So congratulations on the energy that you realize it's going to take to be this type of professional. Congratulations on understanding that, you know, you're not just treating your patients, you're treating their family members because they love those patients, right? And that you wear so many different hats. One of your hats is going to be as an educator. It's probably going to be one of your biggest hats, you know, that you have on. So it's daunting. It really, really is. And I am just really humbled to be a part of what you guys are going to be doing. So anyway, let's get started. And I have to do the business part first, so sorry about that. But here's your syllabus. This is a legally binding document. I've posted it, I've handed it out to you today. On the last page, there's a contract that you would sign. If you decide that you like this contract and you want to stay in this course, and please let me say this, if you decide that you can't meet the requirements of this course, it is no, you know, there's nothing shameful about that. You just will drop the class. And that's, I mean, that's fine. But I feel like people should really be explaining to you all that the syllabus for any course is a legally binding document. This is to help you as well as to inform you about what's required in the course. So I know you can read. I'm never going to read your PowerPoints. God, how many of you have been in those classes where the PowerPoints lose their power and their point because somebody's reading them? I'm not doing that. But I do use them just to keep me honest and make sure I don't forget anything I'm supposed to be telling you guys. I won't read this to you, but I want to bring it because it's up to you. If you sign this contract, it means that you've read it and you understand what's required in the class. Attendance is required. This BCCS policy is that if you miss more than 20%, it's an automatic failure. For this is not really something that I have a whole lot to say about this. But anyway, so I expect you to be here. I expect you to be ready every day. There will never be another day that you come in this class that at 9 o'clock your tables will be cleared with just a cover sheet with nothing written on it, no doodles. If there's a doodle on your cover sheet, you get a 0 that day. A clear cover sheet, whatever you're writing with, and all your books under the table, because every day at 9 o'clock you'll be tested in here. Every day. Every day you'll be ready for a lecture quiz on what we previously lectured. So that means Thursday morning at 9 o'clock, you all are ready at 9 o'clock. I'll be here. If I'm late, I'll give you points. How about that? I won't be. I say that. I might be. Now that I said that, I'm getting more superstitious. But anyway, I just expect you to be ready. And when I say I want you to know what's on the last lecture, what we last lectured, it means that I'm going to give you about 10 questions that are some of them are fill in the blank, some of them are describe questions, distinguish between, those types of questions. You'll either know it or you won't, and it won't be anything that we did not talk about. Am I telling the truth? Am I telling the truth, Jenny? They've had the other sections out of on the sequence. If I give you a question on those lecture quizzes at 9 o'clock that I usually give you 5 minutes to take, because you either know it or you don't. And so you're going to have to be passing them in. 10 questions. You won't know what 10 questions, so that means you have to know everything that we talked about. Because I understand that sometimes you'll be thinking, there are 2 on here that I just can't come up with, but I know a dozen other things. I get that that's going to happen. I understand that. You shouldn't feel badly about it, but here's what you need to know as we're going along. And after the first few, you'll get this. Know everything that we talked about in lecture. When you come in and take those lecture quizzes, you'll hand them in and we'll go over them immediately. So you'll kind of know how you did, right? I'll give them back to you the next time we meet. And you will use them to study for your test. Your tests are going to be from the lectures. So if you've been keeping up knowing, not memorizing, knowing what we lectured about and staying up with this class, the tests are multiple choice. They usually are 3 or 4 chapters of information, but they're multiple choice questions. You just have to review study for those tests, right? There's a couple of other things on the test too, but I'll talk to you more about that, and it's in the syllabus, but I'll talk to you more about that when we get there. So a lecture quiz every day at 9 o'clock, unless we have a test scheduled at 9 o'clock. Don't email me about, is there a lecture quiz today? Because will there be one? Yes. Sometimes you will have a lecture quiz and a lab quiz. Both. But here's the thing. This is a contract class, and I expect you to understand that and be prepared every day you come in. Is that fair? Anybody leaving that? Don't leave. It sounds worse than it is. It's really, let me just say this. I have one of the highest pass rates of AAP of any courses. Do you know why? Because you don't have just 4 tests. If y'all just had 4 tests in here, what did I say about human nature? You have a ton on you. Don't think that I'm not humbled by you being in here. I know you're working full time. I know you have crazy responsibilities. I know this is a burden to be here and the time that you need to study for it. I get that. But because of keeping you on task, people pass the class. So it's like that switch thing again. Yes?
Is it okay if I step up for a second and get
You would have your phone off coming in here. So we're adults. If you have to leave, you have to leave. If you don't want to disturb the entire class, if you have to leave, have those phones off the next time you come in here. That's your warning. First warning. Okay, so as I said, because when people come in late, they're stealing y'all's time, and I am just a tiger about y'all's time, a mama tiger. I don't want people interrupting you, Jamie. And Aaron, I don't want somebody's phone buzzing behind you and you think to yourself, that woman's going to go off on them. So you're sitting there stressed, right? If that happened, maybe you wouldn't be, but I would be if somebody took me. So I'm in here with you guys doing this, and I'm really going to try my best to make sure you get everything you need by the end of this. That doesn't mean we're all going to end at the same level. Some of you, your grades are going to reflect that you've really got this down. Some of you, your grades might not reflect it, but you intuitively might be better critical thinkers. Do you get what I mean? Than the people who have the straight A's. So I'm not saying that we all need to have A's at the end of this. I'm not saying that. What I'm saying is that you understand that we do need to have a minimal type of competency. And then I consider the fact that you understand the profession you're going into. You're going to continue to study even after you never see me again. You're maybe going to keep these books and you're going to continue to study. It is when I say it's a journey, I know that was corny, but it is a journey. It is. I worked in healthcare for 15 years. I can't tell you how many people that I would see that I realized had different foundational knowledge that came in. And I really felt a little bit sorry for them that they had maybe not been either given what they needed or pushed hard enough to get what they needed to be at the level they were. I felt sorry for them, but I felt even more sorry for the patients. So I'm just letting you know, this is a journey. You all take that challenge and realize that you're never going to know it all. You aren't. I'm learning all the time. So anyway, lecture quizzes, they are going to count significantly, like 20+% of your grades. You can't blow those off. If you miss or if you're late, and I mean 9:01, if you come in after 9 o'clock, even if you come in at 9:01, it's 0. You can be late or absent twice because I'm going to drop 2. But after that, those zeros are going to start hurting you. That's just basic math, right? So you can't blow off those lecture quizzes. Those are things you need to be prepared for, and you need to be here on time, just like it's a job. If you're late for your job, I don't know about your boss, but I'd fire you. So that's just life. Okay, so treat this class not like a class that you've had in the past. This is a job. This is a contract, right? So tests are going to be multiple choice. As I said, usually 3 or 4 chapters are going to be on a test. You will have plenty of time. I'll give you more than a week's notice that a test is coming up. You'll kind of know because we're finishing maybe that next third chapter or whatever. But I'll give you dates on when the test and the lab quizzes are going to happen. If you miss a lab quiz or you miss a test, you should make it up before the next class period. So that means come to my office. If you don't know where it is, it'd be a good thing to find out today. Come to my office by 8 o'clock before the next class period and sit there and take it for me, okay? So you have to make up labs and tests. You have to. Lecture quizzes, you don't get to, okay? Any questions about that? I have a different grading scale. The reason I have a different grading scale is several reasons. But one of the reasons is in health professions, and in health profession, if you have 80%, you're passing, you can go forward. If you have a 79.9, you're out. I mean, you're out. 0.1, done. Try again. So I want you all to get used to the fact that an 80% is really, in any health profession, kind of a minimal, bar. Now, that's not in my class. You can see you can get a little bit below that. But what I want you to kind of get used to the understanding that this is not a class where you're crossing T's and dotting I's. You really need to know this, and you need to know it at a certain competency, right? So another reason is because I don't give y'all just 4 tests. That 10-point college grading scale is based on lazy professors. And I did say that on the recording. You can let somebody listen to it. It's based on lazy professors because I've been in classes. I had a science class once that had 1 final exam. 1. That's all we had. But y'all have probably been in classes where you had 4 tests and that was kind of it, right? So if somebody does that in a course, they have to build in a margin of error in their testing tools, meaning that we understand that not all test questions are great questions. So we build in these margin of errors. I'm not just giving y'all 4 tests. You're going to have at least 5 tests in here, possibly 6. And then you're going to have tons of lecture quizzes and lab quizzes. You're going to have a lot of things that are going to help you to evaluate how much you know in this class. And because you have so many testing tools, that narrows the margin of error, how much you know, right? So that's one of the reasons that I do that, but also because you need to get used to that 6-point grading scale that most health professions have. Do you have any questions for me? That sounded so serious. Okay. Yeah, it's not as bad as maybe it sounds. But anyway, I will expect you to sign this today, David, and not now, but at the end of today, and give it to me before you actually leave today. And I will count this as your attendance for today. So you'll see that you actually are going to get a quiz grade for just turning this in and being here this morning. I really appreciate you guys being here. So anatomy and physiology, right? Anatomy and physiology. What is anatomy and physiology? What is anatomy and physiology? You know, you can take these classes separately. You can take human anatomy and you can take human physiology, and they separate them. But most places now are actually, most educational institutions are combining, especially this foundation course that we have, anatomy and physiology together. But tell me what anatomy is. Who's got an idea of what anatomy is? Well, I'm hearing it. What y'all say? Say that. So study of the structure. So are you saying that if you had walked in here this morning and you saw ears on that table and big toes on that table, and maybe, I don't know, nose is here, you would have had, from the structure, you would have a name for that, right? And not only that, but and that is true. It's the study of structure and form, but also where they're located, where they should be in situ, right? So where they should be. Are any two people exactly alike? No. And if that isn't just awesome to you, you weren't listening. But no two people are exactly alike. But we know where to expect to find ears, right? And where to expect to find a nose. So absolutely, that's what anatomy is. And when did you start studying anatomy? When did you start that?
When you were little,
Like how little?
like when you were 2.
Mm.
When you learned to talk.
Even before you were talking, somebody would say, pat your head. Your hand could hardly get there, but you know, because their little arms are so little. So anyway, or clap your hands or stick out your tongue. So even before the Broca's area and the brain was developing for language, you understood language and you understood what kind of response you got for that. So anatomy, let me challenge you all to something. Our labs, after the first two, now the first 2 lab quizzes aren't purely anatomy, but after the first 2 lab quizzes, it's purely anatomy, meaning that you are just seeing a structure, knowing the name for it, and knowing where it should be located. Guys, that's elementary. Your lab percentage grade should help you bring up your class grade by an entire letter grade. If you don't have an A for lab, that's just strictly on you, because it means you didn't put the time in for that. And okay, I'm just saying, because you started studying anatomy a long time ago. Now the fact is, it takes time, because you all are going to have to learn a whole lot of bones in this class, in this section, and a lot of muscles. So is it going to be time intensive? Yes, it is. But if you will do your part with that, there's nothing hard about it. So what is physiology? So I don't want anybody complaining about how hard those muscles or bones are, because I told you there's nothing hard about that. That's just time, isn't it? So anyway, what about physiology? What is physiology?
Function.
It's a study of function. So how does that form work is what physiology is. So how does that ear, why is an ear shaped differently than a nose, right? So how does that form actually function? So physiology is often considered to be the most difficult part. Understanding how something is functioning is often considered to be the most difficult part of anatomy and physiology, but I would dare say that not really, because they go right hand in hand. Structure will always dictate function. Structure will always dictate function. And am I talking about just at a macroscopic level, things that we can see with our eyes? Am I talking about just like the shell formation of the ear, sending sound waves into that auditory canal? Or am I talking about at every level? I mean every level. Every level we'll see, even at an atomic level, that structure dictates function. And you know what? We can beat ourselves, our heads against a wall and try to just memorize stuff because some fool told you you had to know it, you know. Or we can make it make sense. And actually what I love about science and what I loved about it from even before I was even taking true science classes, what I loved about it is that it makes so much sense. It's so easy. You know, y'all have all heard that the easy answer is the answer. Well, that's usually true. That's usually true, and especially in science. So I really want you all to get that. Now remember, I've started talking here, so anything we talk about, could you have a question about it? On it? Okay, so as long as you know that. Now what is science? What is science? Y'all, how many of you taken science classes? You're in one right now. But how many of you taken a lot of science classes in your life? A lot. What is science? Tell me what it is. I'm changing this picture just because I'm tired of it, but I'll come back to it. I will. What is science? What is science? Tell me, somebody. You've got an idea about what science is? Science? Come on now. We're all friends. Who wants to tell me what they think science is? What? You've taken tons of science classes. Nobody in the science class has told you what science is.
It's theories of, it's like a hypothesis of trying to see if it's true or not.
Okay, so good. So science is a way that you can ask questions and test things and find out answers. Is that what you mean? Is that what you said? I think that's what you said. Is that what you said?
Yeah.
That's exactly right. Science is a way that we can ask questions about things we've observed, test those questions, and come up with answers. What could be more fun than that, right? What could be more fun than that? So under the umbrella of science, you know, you have biology. Biology would be the study of life, right? You have chemistry, and chemistry would be that study of elements, atoms of elements that make up all living and non-living things, right? Chemistry. We have physics. Bless their hearts. No, right. So we have physics. How many of you taking physics? I'll talk about physics some here, but okay. So we have a lot of different things under that heading of science. And what science is a way to answer questions about the natural world. The natural world. And I need you all to understand that you can consider that a limitation of science. I wouldn't consider it a limitation of science. I would just consider it that is what science is. It's about answering questions about the natural world. Scientists have never or should never proclaim to be even, well, they might be concerned personally in another part of their life, but nothing about things that can't be tested, about the natural world. Scientists are dealing with that, right? Is that right? So, right, and human anatomy and physiology is one of those very specialized topics under biology. You know, so under biology, you have a ton of topics as well. So that's what science is, and that's what we're going to be studying. Now, as far as human anatomy and physiology, I'd love to start right there because, you know, is there anything cuter than that? So, okay. But would that make any sense to start there? It makes no sense to start with an organism. It would make no sense because the organism is made of what? Things. You know, things, right? So something's made of. Now, what we know about humans is that a human organism can only be healthy if all of the organ systems are present and are functioning. So what do I mean when I say organ systems? I mean, let's give some examples. Y'all want to know some of these examples. They're showing you right here part of the digestive system, not even all of it, but part of it. So an organ system would be like digestive system, cardiovascular system, reproductive system, the nervous system. Those are organ systems. And must they all be present? And should they be functioning? Right, so they should be, but wait a minute. What organ systems? That means we have to know all the organs that are within that organ system. To know if it's functioning or not, we would have to know each organ that's part of that organ system and how each of those organs function to understand the organ system. So that makes sense to you, doesn't it? So like the stomach, the small intestines, the colon or large intestines, that they're part, there's a few of many other organs that are part of the digestive system. But wait a minute, an organ is made of something, isn't that right? So what is it made of? So okay, the answers are behind. So yeah, they're made of tissues. They're made of tissues, and here's what I need you to know. There are 4 basic categories of tissues in humans, 4 basic categories of of tissues, just 4, and you can just write down 4 right now. I'll give you a couple of examples. Muscle is a special tissue type, and nervous tissue is a special tissue type. And so those are just 2 of the 4 examples right now, but you'll be ready. You'll have heard that. And so what we know is organs are made of 2 or more tissue types. It's usually, an organ usually is made of all 4 of them. But it's got to be considered an organ. It's got to be made of 2 or more tissue types. But wait a minute, what are tissues made of? Cells. There are more than 200 different types of human cells. More than 200 different types of human cells. So that's something I would want you to know. Now, are you going to have to know the names of all of them? No. No. But what I want you to know is that cells make up tissues. Very special kinds of cells will come together and communicate with each other to make up a tissue. How many tissue types? 4, right? So these cells. The study of cells is called cytology, C-Y-T, and I don't think you spell for you, but anyway, C-Y-T, we'll see it in your notes later. But ology at the end always means study of, cytology, study of cells. So a cytologist is someone who really is an expert on cellular biology, right? A cytologist. The study of tissues is called histology, H-I-S-T-O-logy. So y'all write that down, make sure you know. The study of tissues. Now, to actually study tissues, we need a microscope because can we really see the tissues that are made of cells? Can we really see cells without a microscope? No. So this is the microscopic study of cells that are making up tissues, is histology. Cytology is the study of the cell itself. Now, here's what I'm going to need y'all to know. Cells, these cells, and there's more than 200 different types of human cells. Cells are the smallest unit that we know that has properties of life. So cells have life. They're alive. Okay. Unless something happens to them and then they die. There's death to the cell, right? So, okay. You're going to know that cells are the smallest thing that have properties of life. Julie. I said this in my micro class yesterday, but I want to just give you all this idea that it isn't so much all about us. Julie, you consider yourself human, don't you? And so you're going to be studying human anatomy and physiology. And we just said that, you know, if you have over 200 different kinds of cells that are going to have their very specialized functions, and some of them are going to come together and make very specialized tissues, and that end up being parts of organs that end up, okay, so y'all are done with that. All right, good, so you're getting that. But Julie, at best, you're about 10% human. Because for every one, and there are trillions, you have trillions of human cells, but for every one human cell you have 10 microbes. For every one human cell, you have 10 microorganisms, microbes. And they are single-celled organisms, microorganisms, and they are alive. Don't doubt it. They are alive. So at best, Julie, we are about 10% human. But here's also something I want you to know. We consider ourselves, and the reason we look three-dimensional and we look with what we can see as human characteristics are because those cells are all coming together to form these tissues that then the tissues begin to become visible, right? And our cells are huge. Our human cells are huge compared to the microorganisms that live in and on us. For every one human cell that you have, and by the way, how many cells did you start off with? 1. You started as one cell. Some people say, no, I did not start as a sperm and an egg. No, you didn't, because you weren't the sperm and you weren't the egg. You were the cell that was formed when the sperm and the egg united. That cell is called a zygote, the Z-Y-G-O-T-E, zygote. You were a zygote. And then what happened to that cell? It divided. And then there were 2. And then those 2 divided. And then there were 4. Okay, I will keep going, but you get the idea. You started as a zygote, and in that cell that was you, there was this molecule inside that cell that's called the signature molecule of all living things. That signature molecule is a huge molecule. It's a macromolecule. That just means a big molecule. And it's called DNA. And never before, that DNA molecule holds recipes for about 25,000 plus genes. Recipes, just like a cookbook. Just like a big cookbook. And inside that cell, that DNA molecule that holds the recipes for all the traits that you have, 25,000 plus, there has never been a cookbook written exactly like yours. And before that one zygote cell can divide two, this recipe book has to make an identical copy of itself so that the two new cells will have the same information. If I were to take a hair follicle from Julie's head, she probably wouldn't appreciate it. But if I were, or cheek cells, or any other cells from any kidney cells, in each of those different cells, different functions, an identical cookbook that should have been identical to the one that was in the zygote. Identical cookbook. We have about 25,000 plus genes. Isn't life awesome? Who needs drugs? Right? Like seriously. No, I'm serious when I say that. It's the same thing, you know, reading Stephen Hawking, if y'all ever read him, or some of these other people read. Oh my God, that was a trip. Okay. All right, I'm back. So let me say this. Those microbes, the diversity of the microorganisms that live in and on you, 10 to 1, they're so diverse. There's so many different ones that make up the garden that you're living in. You're not just providing a place for their garden. You're living in their garden. They have more than 100 times the genes than we do. So at best, you're 10% human, but more likely about 1%. And if those microbes get out of balance, if those gardens get too disturbed, do you get to be healthy? You don't. We're going to talk more about that. This class is really human anatomy and physiology, so we talk a lot about that. But you all cannot forget there's no such thing as a state of health and well-being unless your microorganisms, your gardens of flora, are doing what they need to be doing. They educate your immune system. They allow for certain nutrients to come in and out of your body. And when somebody tells you you are what you eat, well, guess what? You are what you eat. But it doesn't mean it's going to be absorbed, because I can swallow something here and it come out unchanged the other way. Don't say it hadn't happened to you. It has, right? What's going to happen to it along the way? Microorganisms are so important. Your skin, you are walking around with a little acid shield barrier, like on Star Trek, that little, what's it called? Oh my God, I love Star Trek. What's that called? You know what I mean? The ship gets protected. What is it?
Force field.
The force field. You have so you have this force field. Guess what's providing it for you? This invisible force field. Guess what's providing it for you? The microorganisms that live on your skin, they're providing what's called an acid mantle. That's just a fancy way of saying a force field that protects you. You have more microorganisms in your mouth than there are people on the planet. And that's not a bad thing. That's a good thing. Now, here's the thing about these microorganisms. Their diversity, how many there are, where they are, matters, right? And we're just learning more and more about that right now. But anyway, every day something new comes out about that, but that's an awesome thing. So cells, those microorganisms are alive. So tell me what's a characteristic of life. What is it? What does it mean to be alive? A cell is alive. What are you talking about? I can take some of your cells and actually, if I give them food in a petri dish, I can keep them alive for a certain amount of time, because there'll be a certain amount of time that, depending on what they've differentiated into, that they will continue to divide. So I can keep them alive there. But what does that mean? What does it mean to be alive? What is the cell doing that's alive? What's the characteristic of life? Would you say?
Breathing.
Oh, a way, respiration, we kind of call that. So a way to take, and what you're really saying when you say that really is to be able to take something from the environment. Cells can do this. They can take things from their external environment, outside the cell, and bring it into the cell and change it into a usable source of energy. That's a pretty good trick, right? So that's a pretty good trick that cells, living cells, can do, and that is a characteristic of life. I call it animation because there's work happening inside cells 24/7. They do not get to rest. There's no smoke breaks or phone breaks. They don't get to rest. Cells don't. If something gets off balance in a cell can die, right? So I want you all to know, and I'm going to go further than this, but I want you to know that human cells, we have complex types of cells. They're called eukaryotic cells, E-U-K-A-R-Y, anyway, eukaryotic, look that up if you want to. It just means that our cells have true nuclei. True nuclei. EU as a prefix always means true. Karyon means nucleus. They have true nuclei. And what it really means to you is that our cells are complex. We have these structures inside of our cells that have very defined functions. So let me give you an example of that. When I say eukaryon, that means a true nucleus. A nucleus is an organelle. So an example of an organelle is a nucleus. This that they're showing you is actually a mitochondria. How many of you remember learning that in elementary school, right? So mitochondria is an example of an organelle. A nucleus is an organelle. Y'all probably have remembered Golgi bodies, right? Or Golgi, you might have been told. So Golgi bodies or apparatus, those are all organelles. Are organelles alive? Is the nucleus alive? Is the Golgi alive? Is the mitochondria alive? No. No. They look different under a microscope because they have different functions. And what do we know structure dictates? Function. So the reason a mitochondria doesn't look like a nucleus is they have very different functions they're doing, and they're not alive. Is the cell dependent on them having their right structure and their function? Absolutely. The cell needs them to be providing the functions that they have. But wait a minute, what is an organelle made of? I know y'all are tired of this game, and I'm about to be done with it. But what is an organelle made of? Molecules, big ones that are made of smaller ones, and molecules are made of atoms, of elements. All right, so here is what I'm needing you all to get. As far as this macromolecule, what do you all know this is an illustration of? It's DNA. I want you to know exactly what DNA stands for and how to spell it. If you miss it, it's going to be 10 points off. Deoxyribonucleic acid. This macromolecule is the signature molecule of all living organisms, whether they are single-cell microbes or whether they are multi-cell complex creatures like us in the animal kingdom. And we are animals, folks. No matter what you've heard before, we are animals. We're in the animal kingdom, aren't we? So this DNA dictates what will go on in a cell, whether it is your little microbe, the bacteria, or the protozoa, or the yeast that live in and on us, or whether it's our own cells. The DNA molecule is dictating, it's holding all of the instructions for everything that will happen in that cell. Not just for when the cell will divide, but also when the cell will die. It's already written. How many cells did you start with? One. What was it called? Let me give you some other information. After it starts to divide up to 2 weeks, it's called that fluid-filled sac that has these cells that are divided. Before they divide, what do they have to make a copy of? This recipe book, the DNA, so that each new cell gets the exact copy, right? That first 2 weeks, it's called a blastocyst. A blastocyst starts with a B, a blastocyst. So see, if you miss lecture, it's not going to be that you don't email me and say, well, what did we cover today? I don't know. Listen to the lecture. I really won't know. I'm going to have to go and write this quiz immediately after lecture, or I will forget what we talked about. That's just me. But anyway, and it might not be just what was on the thing, because I'll add other stuff. And I'll remember that I added other stuff, so I will put it on the quiz. So the first 2 weeks is called the blastocyst. After the second week to the 8th week, does anybody know what that newly developing organism is called? From 2 to 8 weeks in the womb. And by the way, it's in the womb now, it's called this, in the uterus. What is this called? An embryo. An embryo. From after the 8th week, the 9th week until birth, what is that called? A fetus. And from birth to 6 weeks old, what is it called? Neonate. So are y'all going to know those parameters? Make sure you know those parameters. Where does the zygote form? In a female's body, where does the zygote form? Where is that happening? Usually right at the mouth of the fallopian tube, right where it's near the ovary, right there is where that zygote forms. Then it's going to have to travel down that fallopian tube, uterine tube, to the uterus. How long does it take usually? About 6 days. Do you have a question, Chris?
Yes.
So we got a zygote, first cell, blastocyst, up to 2 weeks, embryo, up to 8 weeks, a fetus to birth, and then a neonate.
That's something that has how do you spell it?
Oh, well, you have to look that up. After you get out, you can use your phone again. So, or look it in the book. You can look it up. So, pardon?
How long the neonate is birth to when?
About 6 weeks. 6 weeks. They call it neonate. Sorry, guys. I don't mean to be snippy about the spelling. Sometimes I'll give it to you just because I see people go, oh, but I can't stand up there and spell it for you. Y'all can Google things and spell. I do. Spelling is important, actually. It really is. I usually will let phonetics go with spelling unless I've told you to know how to spell it, which I just told you something you needed to know how to spell. What was it? Yeah, exactly. Yeah. Other things, phonetics will sometimes count, but y'all should really work on spelling too, and myself included. I work. Some days, have y'all figured out that some days you can spell and some days you can't? Like, what the hell is that? Okay, so it's just like, and I think to myself, wow, I was so good spelling yesterday. But anyway, so fine. DNA is dictating that, and so we know that at about the 6th day, it is going to potentially get to the uterus and implant, right? And implant an embryo up until that 2nd week. Guys, have you all ever heard of stem cell research? What do you know about it? Because we're talking about cells here. What do you know about stem cell research? What is a stem cell? What is a stem cell? You've heard about embryonic stem cells.
I know you heard about the umbilical cord a lot of times.
You can get stem cells from an umbilical cord. You absolutely can get stem cells from the neonate, from the umbilical cord. You really can. But what are stem cells?
It mimics what you need it to be, right?
What'd you say?
It mimics what you need it to be.
It mimics. Okay, so these, can I just okay, so, and then, look, there are a lot of ways you can say it. There are a lot of ways you can say things. If y'all give me textbook definitions, I'll think you'll get credit, and I'll think, bless their hearts, they didn't know what they were talking about. But if you can paraphrase something and say it in about 4 different ways, or explain it to somebody, Aaron, that you see on the street that knew nothing about it, but you could explain it to them so they kind of understood it, that means you know it. Now, if you go to somebody on the street and give a textbook definition, a lot of times they don't know what you're talking about, right? But so let me tell you just in some words what a stem cell is. I just told you that you started as one cell, and those cells start to divide. And then I told you as an organism, you end up with very differentiated cells. Cells that have differentiated to become skin, differentiated meaning maturing, deciding, defined as to what they become. Some will become nervous tissue, some will become muscle tissue. So what happened? What happened from that first recipe book that cells started to divide, and then all of a sudden they started to take on specific jobs, right? That's called differentiating. The earlier the cell, the more potential the cell has to become what you need it to be. So a stem cell is an early, undifferentiated cell that has the potential to become what you need. Y'all are writing longhand, bless your hearts. Okay. So you could say a stem cell is an early cell. You could say a stem cell hasn't differentiated. You could say a stem cell has the potential to become. Now, how does your body know what you need? How does a stem cell know what to become? You got this stem cell that has got the rest. Did y'all hear me say that every cell that I got from Julie right here had the entire recipe book? But as Julie was developing, the DNA was starting in certain cells, was starting to open up to very specific chapters. Some of those cells opened up and they were going to become nervous system tissue, and that's all they're going to be able to do after they've done that. Sure, the whole recipe book's there, but they have decided where they're becoming. Some of the cells, kidney cells, would have opened to a different chapter. Do you get what I mean? That's called differentiated. Is the entire recipe book there? Yes. But once a cell has decided or differentiated into what it's going to mature into, then usually there's no going back and changing it. But what about a stem cell? A stem cell that hasn't decided. And you've got something that you need. Maybe you need a red blood cell because maybe you're bleeding out somewhere. And this stem cell it could become any type of blood cell, any type of the many different white blood cells that you have. It could become a platelet, it's a stem cell. It could become a red cell. But because of what it perceives in the external environment on its membrane, it's going to get a signal that no, you stem cell need to become a red blood cell. And so it becomes what you need because it gets a signal from you, from the environment, as to what to become. Wouldn't it just be like crazy if it just got to become whatever it chose, right? It doesn't. It becomes what you need. So when you talk about stem cell research, when you talk about stem cell research and you talk about stem cells, using stem cells for treatment, typically all you need to do is just present them to the person that is in need, and those stem cells will become what they need. We have some mature cells that cannot repair themselves. Let me give you some examples. Like skeletal muscle, as long as it's not just completely crushed or destroyed, it can regenerate and it can repair. But can cardiac muscle repair itself? No. But what would happen if you put some stem cells in there? Could they repair? Could they actually become mature muscle, cardiac muscle? Yeah, and that's actually been done. So a lot of this has been done. Embryonic stem cell research has never happened. That is and I want you, don't y'all, hey, by the way, never believe any crazy person in front of the room in front of you. Don't believe, because people are just human. Don't believe anything you hear from people. Do your own research, okay? And I would say that definitely. But here is the thing. There has never been an embryo that was aborted for stem cell research. Never. Unless it's some like crazy Frankenstein lab happening somewhere. Never in any legitimate places that happen. That is used to inflame people's passions and emotions. It's never happened. What they have used are cells that were introduced in petri dishes, never been in a female's womb, ever. And the cells fed and they're divided. They have been used. They call them that. But they haven't been. Do y'all know what an embryo is now? Y'all know what a real embryo is? An embryo it has implanted in the uterus from the 6th to the 2nd week, right? Or excuse me, an embryo from the 2nd week to the 8th week. That's what an embryo is. Most of those cells that are being used for stem cells are actually blastocysts, if you really want to be technical about where they are in their development, right? But anyway, so have people taken stem cells from the umbilical cords for the neonates? Yes, absolutely. And you can save them now. You can save those stem cells. What would be the reason for doing that? Has anybody gotten to do that? Yeah. Huh?
I had the option.
You had the option to do it. It wasn't an option when my kids were doing it because it would have been an option. I'm not that old. Well, I am that old, but I waited that long to have kids, so I had the option too, but it would have been like $20,000 a child. So I didn't have the option. But anyway, it's awesome because your stem cells, Julie, have external markers that are uniquely yours. If you ever had to get a transplant from somebody else, even if it was stem cell transplant from somebody else, their markers on the outside look foreign to your immune system cells. So you would have to suppress your immune system for the rest of your life. But what would happen if they had saved your stem cells from the umbilical cord and they could give you a transplant from your own stem cells? Then your immune system it welcomes them because they're self, right? So that would be a reason for wanting to do, your own stem cells. But I'm getting a little ahead of it. But anyway, I'm going to give y'all a break in a second. Now look, guys, so let me say this to you guys. So macromolecules, organelles we said aren't alive. They have to be, it's the cell that has work happening. These have functions inside, but they're not alive on their own. DNA we gave as an example. Molecules are two or more elements that have come together to play that make up these macromolecules, and they're made of atoms of elements. Elements, like the periodic table, those boxes on the periodic table, atoms of elements are the smallest things that we know that have their own unique properties. Are they alive? No, they're not. And how and why atoms of different elements will play or not with each other is called chemistry. Now I'm going to say something that I think is crazy profound, and you best hear it because it's true. But before I say it, let me ask you, how many of you love chemistry, studying chemistry? How many of you love it? It's your favorite thing. Okay, I usually have one in the class. So most people, Chris, really don't love chemistry a whole lot, but I think it's amazing too. But let me say this to you guys. All disease of any living organism is at this level, molecular and cellular level. That's where all disease is. So you can be resistant about wanting to get where we're gonna start, and guess where we're gonna start? After this introduction chapter, guess where we start with what? Chemistry, don't we? You can be resistant about it and think, I'm just gonna get through that. But no, try to embrace it because all disease is at this level. And you can't truly understand how humans function unless you know what they're really made of, right? And how the functions, the structures of these molecules dictate the functions, okay? So I'm going to have you know this hierarchy really, really well. And let's take just a 10-minute break, if you will, if you don't mind. Let's take a 10-minute break so we can come back, okay? So y'all can go out and check your own information. How many of you know you feel anxiety when you don't have your own computer? We know that people do. So, all right, so 10 minutes. You can stand. Is anybody getting up? Okay, you can get up. Sorry. Did I just do that? I'm sorry. Okay, guys, so we're back. Just a couple of comments and whatever before we start back this. I do want to let you all know these courses, they're condensed. So this is why it's going to feel kind of brutal to y'all being so long on Tuesdays and Thursdays. They are condensed, so we're here together for quite a bit of time on those days. So we finish this course right before spring break, and then those of you that are staying for the second part of this will finish up 8 credits of anatomy and physiology in 1 semester. So we do have a lot of time together. They are 4-credit courses, 4 credits. So usually that means like 4 credit hours a week. But for us, that's like 8 now because we've condensed it. So usually we'll be done by about 1, but I'm here available to you until after that too. And I think it's like 2:45, but I'm actually here later than that. I have no life. But anyway, but usually you can count on that as far as your schedule. And sometimes y'all are going to have to miss. Sometimes you're going to have to get up and go. And sometimes you have to. You have to get out and do it. I get it. You know, it's just fine. I mean, you'll have to. But you should sort of try to count on from 9 to 1 on Tuesdays and Thursdays here. Fair? There's also, I was going to try to show it to you, but I can't today. Hopefully you're not having trouble with Canvas. I have just this morning, right before class, put up under your modules in Canvas a lecture recording module that you'll see these recordings come in late in the afternoon of that lecture day, and they're just going to be by date. You'll see the date, so you would click on that. And it really takes you to a YouTube recording. And then the other thing I was going to tell you about that I did was that part of that lecture quiz grade is something called your study reviews that you do. And they're due, even if you miss, because you can listen to the lecture, they're due before 9 o'clock the next time that we meet. So that's on, and it's going to be discussion. And again, those discussions are going to be by dates. So like today's date, you would click on it. And what I want you to do for those is take your notes and come up with questions that you think, you can make them in question form, or you could just do it in fact form, write facts. But do 10 maximum. And the reason I want you to do 10 maximum and then submit it, and you get grades for that. So you're going to get grades for doing that. It's about 5% of your grade in this class, so don't not do it because that's significant. The reason I want you to do it is because when you hit submit, you're going to get to see whoever else has published theirs. Now, if you're the first one, obviously don't have anybody else that's published that. But what you might want to do is before you come in the next time, look at some other people's, because looking at theirs, would that help you study for the lecture quiz? Certainly it would. I have some students who just do 10 facts. Just write down 10 facts from lecture that they learned. And I have other students who do it like a quiz. So they will do a fill in the blank or true false or whatever, and then they have the answers afterwards following. If you do it as a question, answer your questions, okay? Either after the question or at the end, okay? Any questions for me about that? I have had students tell me that did that. This is the first time I've done this, was last fall. And so I've had some students who had never done this before, but they've been in other sections and they were like, I wish you had done that before because I think that would have really helped me. Other students' study guides were helping them. Do you get what I mean? So the reason I don't want you to do any more than 10 is because what I noticed, I didn't give that limit. And I noticed in the fall that I had a student who did her entire notes as a study guide. And I'm going to tell you, I was impressed with what we covered in class. I was like, I don't know. So, I was like, oh my God. And then I realized that some of the students were just putting up anything because all they were trying to do was to get the grades. Do you get what I mean? They were just trying to get hers. I don't want you doing more than 10, even though I know you can come up with more than 10. Do you have a question, Jolanda? Is it Jolander? Jolanda. Okay. Jojo. Okay.
So it's going to be in the discussion part.
Yeah, so I just created it. It's under modules. You click on modules, and under the modules, you'll see the syllabus, you'll see lecture recordings, and then you see discussion board and a date. So you would just click on like the date and do it and put your little template, whatever, before the next time we meet.
All right.
Fair enough?
Fair.
And as soon as you hit submit, you should be able to see whoever's already posted, but not until then. Also, I have something that is not going to start this week, but will start next week, and that's y'all's visible body code that you had to buy. Does anybody have that code with them? That just the, and you don't have to open it. Hold it up, if you will, for me, Maya. Y'all had to purchase that. Sorry, I know it's like $66 something. But when you're ready, and I haven't given you this course number yet, I'm going to also post that under modules, and I'm going to say this is your visible body course code. You all will go open that up. You will register through Visible Body, and when you register, they're going to ask you for that course code, okay? And you will put that course code in, but I haven't given it to you yet. It will be posted, though, under the modules in Canvas. Let me say this to you guys. That thing that you just bought with Visible Body, you own that now. It's like having like you can download that to your computer and you have it. But for 2 years, any course that uses that, you can go into, you don't have to repurchase it. So So that justifies maybe the $66. So we will be using it through the entire 8 credits here. We will be using it this semester, and it's lab. It's for lab, okay? We'll be using it in lab, and we'll be using it in AMP1 and AMP2 as well, okay? So just hold on to that for now, because I haven't given you all the course, I haven't posted that yet. I'll have it posted about Thursday, and I'll remind you all that it's up, and y'all can go ahead and start playing with it. The lab that we have today is one that I'm doing for you. I'm giving it to you. It's not something you have to go online and do. Okay? All right, so any other questions? There were some good comments I was hearing as I was walking along. Any other questions for me before we continue? All right. So what we know is it's daunting. It is a daunting task to learn human anatomy and physiology. So don't try to put that cart before the horse. Let's just, I guarantee you all that I don't quiz you on anything we didn't talk about in lecture quizzes. So take it by that, okay? I guarantee you, relax, all right? So truly, and it's daunting, but we'll get there, and you'll be surprised how much, I think you'll be surprised how much you think you know at the end of this semester. At least I hope you'll be happy about that. So anyway, we do understand that when you woke up this morning, somebody right before you became, you awakened, you could have had vital signs being taken. Blood pressure, respiration, right, oxygen, sats, you could have had all those vital signs taken. But as soon as you opened your eyes, do you think they would have stayed the same? Why not?
Because you were arrested.
So you would have, your mind plays a huge part in how things change in the body. Everything's changing, right? Just with even with your state of consciousness, things have changed. But then how about if you sat up and stood up? What would have had to have happened to your blood pressure? It better accommodate that, or you're going to hit the floor, right? So everything, nothing is ever the same in a living system. In a living system, which we said our cells are, that are all communicating with each other, sometimes better than other times, but they're all communicating. These cells are constantly, things are going up, they're going down, they're constantly changing because of response to the external and internal environments of the cells. So they better be able to do that. Staying in a state of balance, staying in those parameters that are within the normal ranges is called homeostasis. And I would want you all to know that you could define that with actually a couple words. One word being balance. Another word being health. In homeostasis, you must stay within the parameters that are considered to be optimal parameters for your cell's well-being. And that's for thousands of things. Let's just think about blood glucose levels. Can they be too high? Can they be too low? They need to be what? Just right. They need to be just right, don't they? And we'll talk about why that would be. I'm going to give you an example of that in a little while. But anyway, yeah, things have to be just right. Can you be too hot? Can you be too cold? Can your blood calcium levels be too high, too low? Yeah, they can. So I talk about living systems as often being like Goldilocks. Things have to be just right. They can't be too high, they can't be too low, they can't be too hot, they can't be too cold. They have to be just right. So even if things seem to be wonderful things, if there's too much of them, they can be deadly. So this is this term homeostasis, staying within healthy parameters. So, you know, really, like back in the day, like how do you learn about complex organisms, individuals, or an organism? How do you learn about that? Well, there's certainly stuff that you can do. And I think that we need to get back to some of it because we've kind of become so, we've learned so much about molecular and cellular biology that now we have to have a laboratory test to tell us what disease is, when sometimes we can actually use body language and we need to be paying attention, right? Paying attention. It's amazing to me, and probably some of you all know this, how many health professionals actually, that you don't even know if they even looked at you when you went in. How many of you have had that happen? Have you had that happen? I hope you haven't, but it wouldn't be unusual if you have had that happen, because now everybody wants the pathology department to do their diagnosing, when really a lot of things are going to be missed that way because body language can tell you so much. and just looking at somebody. So observational skills, inspection, observational skills, head to toe assessments. We're not doing them enough. Head to toe assessments, inspections. Now, I want you to know these definitions. You may already know them, but if you don't, you will need to know them. You can, there's something called palpation and auscultation and percussion. Palpation is touching. Auscultation is listening. And percussion kind of uses both. You're listening for like rebound and echo, if you will. But these are things you can do. And there is this saying that you do not palpate until you've auscultated. Have you heard that before? You want to be inspecting and listening before you start pushing on somebody's abdomen. Can you hurt somebody that way? If there's a blockage, you can. So, but these are ways that we can do that, examining body, but certainly cadaver dissections are one of the best ways to actually really learn human anatomy. I have this software, it's called the Reveal software. I have this software that you can use in lab, and I'll have my laptop that you can use it. You can also, I think it's gotten really inexpensive. You can purchase it where they have a couple of cadavers, an adult and then also infants, where you can actually, using your mouse with this software, you can go from superficial to the deepest. The coolest thing about cadaver software, which is really cooler than cadavers, I know y'all don't believe that, but it's true, is that these cadavers on the software, and I say this and I have to preface it with, I don't mean it the way it sounds, but these are recent, fresh cadavers. See, cadavers that you have in labs have been exposed to chemicals, harsh chemicals and preservatives, and they don't look normal anymore. I mean, it might be cool to the students to think that they're working on a cadaver, but it doesn't look natural. These were recent. And so what they have done is taken thousands of pictures, as they have used amazing instruments that are just beautiful instruments that they haven't torn even thin superficial muscles. They've done just a beautiful job. And the thing is, you can see these superficial muscles like the platysma, but deep to that is the sternocleidomastoid, which y'all will know soon. But anyway, you can, unlike a cadaver where you might have seen it, but you probably cut it all to pieces as you were doing it. You can't put it back and do it again. But you can on the software. You can go back and do it again, and look at it again, going from superficial all the way to deep. So human cadavers are better than cats. They're better than rats. We do have rats. They're better than individual organs, which we do have a lot of comparative species organs that we'll be using in lab. And I have some human specimens as well. But honestly, this is a great way to do this. Your visible body is awesome. That technology is awesome. I'm sorry I have to pay for it, but anyway, it's an awesome tool. Now, what we have too is, and I don't think anybody in here is old enough to remember this, but it used to be not uncommon that people would do exploratory surgery. So somebody had gone in, we didn't have they call it non-invasive. It's a little bit invasive. Medical imaging, so they didn't have the CAT scans or MRIs. So they had to open you up. And they opened you up. So this would have been a way that, and it's still done sometimes because you have to. But anyway, but usually it's sort of a last resort. Medical imaging is called non-invasive medical imaging because truly you're scanning and you're trying to take these pictures. And some of them can give you a really good three-dimensional look inside the body. So much information now is gathered from CT scans and MRIs, and we'll talk a little bit more about that later. But this branch is called radiology, and I know y'all have heard of this. Gross anatomy is a term that's used with when you're talking about structures that you can see with the naked eye. Please don't think it's about gross things. I had somebody tell me that once, and on a quiz question, they said, it's just weird, it's really disgusting. No, it isn't. It's what you get. Nothing about the human body is disgusting. Okay. No, it's not. And so it's just what you can see with the naked eye. I would take students, and I might try to do that this semester because I haven't gone in a couple of years now, to UVA for a gross anatomical autopsy conference. So if I can schedule that for late May, y'all's group that do A&P 1 and 2 would be the perfect group to take because y'all have just had concentrated A&P. And so you guys, I'll try to schedule that. And what it means is every Wednesday they have gross anatomical autopsy conferences at UVA where the interns in pathology are justifying the cause of death that they're giving to the attendants for the people the patients that they had that week that had died. And so they come in and they do that for their attendings. And then usually at the end, we can sit and listen to what their presentations. And then at the end, and they usually bring in the organs, you know, and stuff, and they justify it. And then at the end, they usually let my students come up and ask questions and, you know, touch whatever they want to touch or look at. So anyway, so we might try to do that. I had given you all definitions of these, had I not? Okay, so great. And histopathology. Pathology is the study of disease. Pathology by itself is the study, just that word, pathology, the study of disease. Pathos is dark, you know, right? Isn't that what pathos means? Dark, evil, whatever. So study of disease. Histopathology is looking at the signs of disease in these tissues. Now, again, this is just showing you some examples. I'm just using this to keep me honest, make sure I don't forget anything. And then obviously there are all these sub-disciplines because so much information is being found out now all the time. And as I said, every day there's just so much stuff coming out. So this is why if you have anything that's at all unusual, you probably need to go to a specialist, isn't that right? So these are just some of the areas that we think about as sub-disciplines of anatomy and physiology. I do want to let you all know, going back to that head-to-toe assessment thing, you guys, I know primary care providers are usually referred to as the MDs or DOs that are taking care of a patient with diagnosing and prescribing, but I'm going to tell you that they aren't the primary care providers. The ones that are the nurses and the EMTs. And they're the ones that are hands-on doing, working with those patients. And so I know that. I know that from my own experience in pathology, because I worked in pathology, but was also liaison with the epidemiology department. So I had a lot of floor experience, and I saw it. So I know that's the case. How many of you doing nursing? Okay. So I'm just going to tell you, you guys are the ones that truly are the primary care providers. Okay. And we will use comparative species. I do want you all to know that Hippocrates, a Greek physician, is considered to be the father of medicine. And you all have all heard of the Hippocratic Oath, haven't you? Where it says that you will do no harm. Essentially, I mean, paraphrase, that's what it's saying, is that you'll do no harm. But the really amazing thing about Hippocrates was Hippocrates, and this was truly amazing, and then everybody forgot it for a couple thousand years. The truly amazing thing was Hippocrates said there's this cause and effect with disease, and we need to be asking questions and researching and figuring out why someone has what they have. There's a cause and effect, and we need to continue this study to do this so that we can maybe, you know, someday not do any harm, right? And certainly this is where we got this Hippocratic Oath from. Look how crazy in Mesopotamia that they used to use herbal salts and physical therapy and whatever to treat people. How crazy is that? Is it? No. When we look historically at how medicine has progressed, we are in a revolution right now because we are learning so much at a molecular and cellular level about disease. But we almost, and most people would accept that we've done this, we got away from the idea, it was all about like diagnosing and treating disease instead of preventing disease. And so what we really need to sort of circle back to is this idea of preventing disease. Yes, we know a lot about where disease is happening and how it's happening and how to treat it now, but we also, with that, learn how we should be treating it, how we should be preventing it. And it's not so crazy to think about this as being used for preventative care. And hopefully people are kind of coming back around to holistic medicine and that holistic approach. So I don't think I asked you anything about Aristotle. If you ever get a chance, if I'm skipping this or y'all, if I don't talk about it, do y'all need it for me? It doesn't mean you should read it. It just means you don't need it for me, okay? And that you can read it, but I'm not going to test you on it, right? So So anyway, father of medicine was who? Hippocrates, right. Guys, the cell theory, this is a scientific theory, all right? This is a scientific theory, and the cell theory says two main things, 2 main points, and I would want you all to know them, paraphrase anyway, it sounds like this, but I would want you to know the first premise of the cell theory says that all life comes from pre-existing cellular life. All life on this planet comes from pre-existing cellular life. And the second premise of the cell theory is that the cell is the smallest unit that we know that has properties of life. I had already told you that, hadn't I? All right. So what that means to you, Janae, is it Janae? Janae, is that you have parents. You know, as a zygote, you were created from parents that contributed DNA. And it means that your parents had what? Parents. And their parents had. Okay, so we can play that game for a long time. And we could go back for a long time. Now, so that's the premise of the cell theory. And that might seem so elementary to you guys. It might seem so elementary that, of course, mice don't come from clean hay in a barn. They don't just spring up. And of course, flies, maggots, don't come off of dead meat. There was a fly that laid some eggs. Is that right? And of course, life doesn't just spring up. Life comes from pre-existing cellular life. This theory, this scientific theory, it took exhaustive studies and experiments over 400 years of people who were questioning about where life comes from, doing exhaustive studies and experiments before it was finally accepted, the cell theory. The cell theory of life was accepted around 1900, and some of you all might be thinking, 1900, like, oh my God, my grandmother lived in 1900, my grandmother, all right? So it wasn't that long ago. Now you might be thinking to yourself, so this is a theory, so a theory just means an idea. Wrong. That's where a lot of science, a lot of people don't understand the difference between science and other classes and other terminology that use theories. Because, you know, we might have a theory about why she's cheating on him or he's cheating on her. That's not the same. A scientific theory is the most exalted explanation after exhaustive research has tried to explain a naturally occurring phenomenon. Are y'all hearing what I'm saying? So I know you couldn't write all that down, but here's all I'm saying to you is a scientific theory is what all the experts, true experts in the field, think is the answer to that naturally occurring phenomenon. And it doesn't happen, scientific theories don't happen overnight. There was over 400 years of people researching this and testing until this finally was accepted as the explanation of where life comes from on the planet. Right? Right. I want you all to know that the cell theory, a couple people are kind of giving credit, but it was really Louis Pasteur. Louis Pasteur. Y'all have probably heard of Louis Pasteur. But Louis Pasteur, around the 1900s, right at the turn of the century, Louis Pasteur did an experiment that put all the others, just shut them up. So in a way, kind of did. And so this was the final cap on it, and the cell theory was accepted by the scientific community as far as where life comes from on the planet. What was the theory that it replaced? The theory of spontaneous generation. The theory of spontaneous generation says life springs from non-life. So from this table, we can get a little koala bear. That would be some good drugs. No. Or from a barn that you put clean hay in, fresh cut hay, mice will come. From that wine that you just made, there's such good wine. It can be spoiled because life will just spring up. You and contaminate your meat and your wines and beer. Okay, whatever. So anyway, that was the theory of spontaneous generation. And some students say, how crazy, and that was just 1900, and really that wasn't that long ago. Why would that have taken so long? That's so crazy. Not really, because in science, we understand you do need to be exhaustive in your testing. You need to not just do it once, the test once, and about something that's naturally occurring, not something that can't be questioned, can't be answered. That's out of the realm of science. And the two shouldn't meet, because science is just about the naturally occurring world. And that's a limitation on science. It's a real true limitation on science, that it's just about the natural world, but that's all it's supposed to be about, and what can be tested. So do I have any questions on that? All right, so the cell theory. Now, why do you think people wanted to hold on to the theory of spontaneous generation? Why do you think, Caitlin?
That's probably all they do.
Well, that's what they knew, and that's what they saw. They saw mice come into the barn, and they saw the meat all of a sudden have maggots, and they hadn't seen the flies laying on it. And that's what they saw, and that's what they knew. And there was also lots of writings that supported the theory that life comes from non-life. And sometimes it's really hard to step out of your comfort zone and accept things that might, so it's like incredibly hard, and it can be challenging. And it can make you feel uncomfortable. It can make you feel unsafe, right? When you hear things like there's usually in the history of the planet, there's been a meteor striking the planet every 20-some million years, and it's been 66 million now since one I said. It can make you stay up at night. Is it going to happen? And so, those are the kind of things that can make you feel uncomfortable. And who wants to feel uncomfortable? Not out, right? So anyway, but that really is the way. It's the same reason. You guys know who Galileo was, right? And Copernicus. What did Copernicus say? What did Copernicus say? Do y'all remember what Copernicus said? Not that anybody cared what he said, because he was considered kind of like a town fool. But what did Copernicus say? Do y'all remember? Do y'all remember those things? Copernicus and Galileo from back in high school. Y'all know. What did Copernicus give us? What did he give us? And actually, he had done sort of exhaustive studies too, and he had a lot of evidence for it, and nobody was believing him because nobody cared about him. But anyway, what did Copernicus say? Yeah, the sun was the center of our solar system, and the Earth was revolving around the sun. It wasn't that everything was revolving around the Earth, and everything on the Earth was revolving around man. So when Copernicus said that, some people got put to death for saying that. When I said put to death, I mean brutally put to death. That's in your history books. Go read it. So, but Copernicus said that, and he had lots of reasons why, and what he said was evidence for it. And then here comes Galileo, who isn't considered the town fool, and Galileo is considered to be, he was revered. He was almost considered to be like a next step up from humans toward, whatever. He was revered and loved, Galileo. Galileo started looking at Copernicus's findings and studying them and trying to repeat some of his research. And Galileo was bold enough to say, guys, Copernicus is right. The Earth is revolving around the sun, not the other way around. There were many that wanted to put him to death. And then the others talked him out of it and ended up putting him for the last 10 years of his life under house arrest. Because it made them feel uncomfortable to have to accept that. So sometimes things can make you feel uncomfortable, but in science, what we need to do is, for scientific theories, and I do need you all to know this about scientific theories, that these aren't going to be like you use the word theory outside of the science class. These are explanatory statements about naturally occurring phenomenon, the natural world, not the spiritual world. It's not supposed to be about the spiritual, just the natural world. Explanatory statements about how something is happening, right? So that's what a scientific theory is. To get to a scientific theory, there has to be exhaustive research and using facts and laws, scientific facts and natural laws, things that we know to happen. You cut arteries, Julie, you've probably seen some people who had cut arteries, and without quick action, what's going to happen?
Bleed out.
They're going to bleed out. That's a natural law. That's going to happen. Their heart's not going to be able to keep pumping. It isn't. So using laws, using facts, using exhaustive research, scientific theories are created. Now, are they beyond a shadow of a doubt? No, because a true scientist would tell you that we're always repeating experiments and we're always open to new data that has to come in. So this might be considered another limitation of science, is that, you know, scientists wouldn't want to tell you that things are proven beyond a shadow of a doubt. They're just telling you what we know today. We're using the best science, right? So please do know that. That is what science is. It's a way that we can do that. So let me give you the steps of the scientific method, because this is what must be used before you could ever think to get to a scientific theory. The scientific method, and you guys, don't memorize these steps. There are going to be a few of you that do, or you memorized it in high school, and you're going to think that was right, so you're going to repeat it. You're going to do it wrong. All right, look, so let me tell you what they are, because they're common sense. You all have used the scientific method steps a dozen times today already, because this is how logical people think. The first step in the scientific method is an observation. An observation has to happen. An observation about something in the natural world. Nothing spiritual, nothing, whatever. In the natural world. An observation is made. From the observation, a question is asked. So the second is question. Observation 1, question 2. We are humans. So what we tend to do when we observe and then question something, we tend to make a statement that answers the question. We tend to do that. Do you know what that statement is called? Hypothesis. Now, if it's something in the natural world and it's a hypothesis, we should be able to test it. And after our test, which was the 4th step, we should have results. You know what's beautiful about science? Is it never matters if your hypothesis is right or wrong. It's all about learning something. And sometimes the learning something really does make you feel uncomfortable. But it should never be. Science is the only class that you can ever truly, or only discipline you can ever be in, that you can be wrong thousands of times. And that's okay, because guess what you've learned hasn't worked. Those thousands of things didn't work. You learned all along the way. Right? You were learning the whole way about it. So what are the steps? Number 1,
Observation.
Then
Question. Hypothesis.
that's just like logical. You wake up, you see that your alarm didn't, you wake up, you notice, you observe your alarm didn't go off. Right? You say, why? And then you make a question. You ask a question, why didn't my alarm go off? And you immediately say, my husband turned it off. Right? So, can you test it? You can ask him. He may be a liar, but you could ask him, and hopefully you would have the result. Right? Whether you have to accept your hypothesis or refuse your hypothesis, right? Reject your hypothesis. But isn't that like logical thinking? Isn't it? With drugs, this happens with drugs all the time now, as far as drugs coming out onto the market. And what primary care providers will notice is that the drug was put out for something, some sign or symptom, but then they'll start noticing that the patients that were on that something that is unrelated, that was an observation. And then they ask a question. The only difference is they've been put on this other drug for this other condition. Is it influencing this parameter? And then they say, I think it is. And could they set up a test? And then could they see that is all what has happened with the Viagra stuff and cardiovascular research. Viagra wasn't for that at first. Does everybody remember what it was for? Okay, so. But I'm just saying, so that actually happens. That happens all the time. We do that. Y'all can think of lots of things. You observed you got in your car and there wasn't enough gas, right? You ask the question, what happened to my gas? So you get what I'm saying. Now look, but in science, though, when you're talking about drugs and when you're talking about disease and when you're talking about climate change and when you're talking about evolution, in science, you can't just do what I just said. In science, you use those steps. But you have to have large numbers in your study. You can't just treat one person with the drug and they get better and say, oh, that drug treats that. You know, you have to have large studies. These are things you would want to know. And before something becomes a scientific theory, there have been large numbers of studies, and usually study subjects. There have been people who didn't have a dog in the fight, meaning scientists that were just as much experts, but they weren't going to get fame or money from the results. They're called peers. They repeated the studies and got the same results. And they had nothing they gained from doing it, right? So peer review, large samples, statistical analysis. You guys have heard that numbers talk? Well, sometimes they lie. And so that's why you get someone outside looking at those same numbers and making sure that that statistical review was done how it needed to be done. And then what else? Blind studies and double-blind studies, especially in medicine. The placebo effect, I mean, you cannot believe. I bartended after, like at the end of college and right afterwards because it was good money back in the day. Y'all can't believe how many people get virgin drinks and get falling down drunk after a couple hours. I did not do that, but I worked with the bartender who did that. And you know what was crazy? He had those same customers always coming in. It was just a study, really, about what the human mind can do. So blind studies. Control groups. These are things y'all would want to know. Makes us have confidence when we get to that fifth step. What was the fifth step? Results. So know some of those things that are going on that gives you confidence in those results, right? It's been repeated by peers that didn't have anything to do with it. Large numbers have been studied. Statistical analysis has been done. Blind and double-blind studies have been done. Double-blind means that even the testers don't know which group is getting which drug. They don't even know because everything's been number-coded blindly. They don't know until the very end. Because sometimes they can influence. They can influence by suggesting that, no, you're not getting a placebo, you're getting the drug, right? And with that influence, maybe you and how you responded to it, possibly it could. So they try to take all of that out. And then you can have, when you get to that fifth step results, you can feel pretty good. Are you ever stopping asking questions? Never. Never. Okay. Yeah, so that's the way it is in science. So I think y'all knew that, and that's fine. And these are what these are going through, these slides are talking about. But facts and natural laws are used to come up with these theories. So another theory that y'all know about is the theory of evolution. You guys, what does the theory of evolution state? Tell me what you know about it. Don't read my slide. What'd you say? Adapt. So evolution means change. It does, and adapt, we know, has something to do with when we think about the theory of evolution. The theory of evolution, though, what does it say? What does it say?
That name came from.
That's the myth.
Okay.
That's a misinformation. That's one of those passionate things that politicians and sometimes I don't even know what these people are trying to do. But that's a myth. That's a myth, and that's one of the biggest myths.
It means that we're always adapting to our environment. Or like.
Well, that sounds like individuals are. Individuals, we should be outside of a science class, outside of science, outside of the theory of evolution. When we use the term that I'm evolving, I'm adapting, I can change, I can meddle. You know, that is their words we use for an individual that has nothing to do with the theory of evolution.
Survival of the fittest.
Survival of the fittest. It is. You know, we talk about survival of the fittest, and then you think that that's related to individuals, but it's really not ever related to individuals. Let me tell you what the theory of evolution states. And by the way, this has been more than exhaustively proven. This is happening in our own bodies with the superbugs that are being created by antibiotics. That is another just little thing that proves the theory of evolution. Evolution states simply this, and no other myths and no other, scary kind of things. And I'm gonna say this to you slowly so you can write it down, but then I'm gonna break it down so you actually understand it, and maybe the misinformation you may give it you'll be able to let go of. Okay? The theory of evolution states that the percentage of traits found within a population will change over time. I'm going to say it again. The theory of evolution states that the percentage of traits found within a population will change over time. All right, now I want to explain to you what that statement actually means, because I think people get confused. Okay, so look, what is a trait? Name some traits. Hair color, eye color, height, right? Skin tone. These are traits, characteristics, traits. There's genes, I've heard that, 25,000 plus genes, that each gene gives a trait. Some of them you can see, some of them are external, you can see on gross anatomy, most you can't. So those are traits. Percentage of traits within a population, you have to know what the population is. A population means all of the individuals within a species, within a location. So like right now, there's a population of Homo sapiens in room 29 at Southside Virginia Community College. There is a population, we are it, right? Aren't we all Homo sapiens? By the way, y'all know that we belong to the genus Homo and the species Sapiens, right? So if you did, make sure you know that. Humans are the only species in that genus. We're the only species in that genus that belongs as Homo sapiens, right? All right, so right now though, we don't have, if we just looked at us here at Southside Virginia Community College in room 29 as a population, which we are, a population of Homo sapiens, would we have the percentage of traits that would be the same as if we took a little colony in Asia somewhere, on an island somewhere? No. It would, those percentage of traits, though, for that population would look different, wouldn't they? Probably, than ours. Right? Are you with me? So what evolution states, and by the way, as a human, I have a population of a bacteria called Escherichia coli. Or let's do one y'all know. Staphylococcus aureus. On my being, we all, and I'm not the only one who has Staph aureus, we all have Staph aureus on our skin and up our noses, we do, and in other places where sun doesn't shine. So this is, we have Staph aureus. I have a population of Staphylococcus aureus along with hundreds of other genus and species of microbes that live in and on me. But let's just talk about my population of Staphylococcus aureus. If I were to take an antibiotic that was targeting my Staph aureus, do you think that the traits that are found in my Staph aureus right now would stay the same after that treatment, after that external insult? No. What can happen is I can lose all the weak ones of my Staph aureus. I can lose all the little weaker ones, but the ones that have the ability to survive that assault, they can remain. And if you remain, guess what you get to do? Survive. You get to divide. And if you divide and divide and divide, and you were the strong ones, now has the traits within my population of Staph aureus changed because of the external environment? Yes. So this whole idea of creating these superbugs that we have created, because of our use of antibiotics, which have saved millions of lives. I'm not saying not to use them, but have saved millions of lives. That's just one tiny, not even a drop in an ocean of evidence that traits within a population traits of a species within a population will change over time. Because guess what we know is always changing, and this is irrefutable. It is always changing. It is always changing from the beginning of studying about time on this planet to right now. What never stays exactly the same? The environment. That's changing all the time, and it's never stayed constant. The environment changes, and the environment pushes the percentage of traits that you find within a population over time. Hey guys, how many of you have been down to Jamestown? Did you get to go to Jamestown? Did you get to see the replicas of the boats, the ships that came over 400 plus years ago? I think that, yeah, over 400 years ago? Yeah, let me tell you, how did you fit on those ships? Did y'all see the actual armor of Christopher Newport, the actual armor? Do you think he was a dwarf in his day, or do you think he was probably pretty average in his day? He looks like a dwarf to us now, and I'm not using that in a derogatory term. I'm using that as a descriptor. He was tiny, and he was in that armor. There's nobody in this class that could fit in that armor. Do you think he was unusual for his day, or do you think his traits, his body size, his height? Have you been on the ships? Do you think the people built ships that they had to walk like this in? We don't build them like that anymore, do we? They didn't build them like that either. The percentage of height in our populations have changed over time. Yeah, it can take a long time. It can take a really long time. But we've had a long time on the planet. I know there's some of you who feel like the Earth is 6,000 years old, but it is not. It is 4.6 billion years old. And if you want to think it is, it's fine. I don't care what you think. But make sure you put down accurate things on the test, okay? The Earth is about 4.6 billion years old, and there has been life on this planet. Actually, new data is kind of coming in to think that it was even before what I'm about to tell you, but it hasn't been proven yet. But we do know life started on this planet approximately 3.8 billion years ago. That's with a B, as in boy. So if you think, and actually new evidence is scientific evidence, not talking about beliefs or things that make you feel warm and fuzzy and cozy, but actual evidence is saying that maybe life was here even earlier than 3.8. But right now, the science is supporting 3.8 billion years. Now, 3.8 billion years ago, do you think the life was like it looks right now? No. The atmosphere was completely crazy harsh, and so were the seas. The primordial atmosphere and seas were so harsh that if we took all except for archaeobacteria, if we took every life form that we know right now, and we were to transport it back 3.8 billion years ago, none of us would last a microsecond. We wouldn't survive that. But what has been changing all that time? The environment. And did the life that got to exist? The life doesn't adapt. It's just that some traits within the species get to survive. And as they survive, if you get to eat and survive, you get to hopefully have sex. And if you get to have sex, you hopefully get to pass the trait to the next generation, right? So you don't want to think about the theory of evolution is that an individual or species adapted. They didn't. It was just that whatever the environment was favoring its traits at that time, they got to survive. And because they got to survive, they got to pass those same traits to the next generation. So what you see in the next generation is more a percentage change of traits in the next generation. The theory of evolution does not say we came from monkeys. How asinine. Because if we did, we'd still be coming from monkeys. Why wouldn't we still be coming from monkeys? Right? The theory of evolution says that the percentage of traits found within populations will change over time. And we always talk about people, but it's not so much about that. Like we said, it's even on the microbial level, isn't it? So height Nutrition, has nutrition changed among humans? Nutrition has changed. Have lifespans changed?
Yeah.
Lifespans have changed, absolutely. So, you know, guys, there's nothing scary about the theory of evolution. It really isn't. There are actual education institutions that won't teach it because they're so afraid of how people. Did you know that in 2019 there are institutions very close to us that won't teach the theory of evolution, won't let it be explained, and will actually continue the myths about the theory. There's nothing scary about it, nothing. And the thing is, we also still want to keep researching and keep whatever, but it is a scientific theory. So anyway, do you have any questions or comments that you'd like to have? Do you have any questions? Can you close that back door? All right. So I do want you to know Charles Darwin was a minister, a very spiritual person. Being a scientist and being spiritual are not mutually exclusive. So Darwin is the one who did, because of his thousands of observations and saving of specimens and looking at different species as he was traveling on a 5-year voyage on that Her Majesty's ship, the Beagle, which he was sick the entire journey, didn't want to go on that journey. His parents made him. So anyway, it was his documentation and observations and that came to that he's given credit for the theory of evolution. So anyway, the theory of evolution, which really kind of states how life has come to be on the planet today. We know that if we were to go back 1 million great grandmothers, if you put 1 million greats in that, would that, and that was one of your descendant from that, would they have very similar traits to you? If we went back 1 million greats? No, not at all. Not at all, probably not at all much. I just told you that 400 years ago, people looked different, didn't they? Didn't they? They looked very different. And that was just 400 years ago. Let's go back a few thousand years. You don't think that people would have maybe been a little hairier, you know, or whatever. I mean, that's just one trait. That's just one trait. And it's not just about us. It's about all life on the planet. I think that's what gets people with the theory of evolution. It's so much like ingrained in their head that it's saying something about them. And it's not. It's about all life on the planet and how we've gotten to the life that we have on this planet. So anyway, and the survival of the fittest is really true. It doesn't mean that, you know, it just means whatever trait is the most fit at this point. You know, I can tell you guys that 1,000+ years ago, looking for a mate, I would have been looking for someone who could run fast and throw a good spear, right? Is that still the same thing we're looking for, ladies? No. No. So are the percentage found within the male population going to change? Did they change over time? They did. And they have, and they will continue to do so because the environment changes. The environment changes, and so the percentage of the traits found within the population of a species in a location will change over time. That's all it says. Okay. So that's the theory of evolution, and I have gotten to this. I told you about this hierarchy that you guys are going to know, and now what I really just like to touch upon is this idea that no two people are exactly alike. So as we learn normal, we will learn normal. We will always keep in mind that even in the normal, there's slight variations and no two people are exactly alike. And sometimes things are very, very different. Some people are born not with 2 kidneys, but with just 1. Is there anybody in here that knows that they just have 1 kidney? No? Did you want to tell us if it was true? But okay, so sometimes that's the case. We will look at comparative species like sheep and cow or whatever for parts, and you'll see that no 2 of them even look alike, right? So it's not just within humans, it's in other species as well. I talked to you about the characteristics of life. I want to give you an example, a definition for metabolism. Metabolism, You can think of metabolism as cellular work. The cell, what kind of work is going on inside the cell. So metabolism is all the chemistry that's happening inside of a cell at any given time. It's a rate that you can actually measure. So y'all have heard of metabolic rates, haven't you? And metabolism just is referring to all of the chemistry that's happening inside of a cell at any given time. Do you think your cells, all of your cells, your many differentiated cells as a developed adult, do you think they all need to be at top speed at all times? Or do you think some of them can slow down a little bit while others of them get more attention, and that there's going to be this whole little juggling thing that has to happen, that needs to happen? Yeah. So, but when you think about metabolism, that's what it's referring to, is all the chemistry, all the chemical reactions that are occurring at any given time. Now, I want to talk to you about homeostasis a little deeper than I did before, and we're about done with lecture. I can say, woo-hoo, okay, and you get a little break. And I do have a short lab I want to introduce you to today. But homeostasis, I need for you all to really get this next part, and I need for you to be able to explain it to me, discuss it or explain it to me. So if you're having any questions about it as we go along, you need to stop me, okay? All right, so I don't think I can have colored pencils, which is really sad. Would anybody know how to read the colored pencils on here? All right, well, okay, I can't figure it out either. All right, look, so when we think about homeostasis, we said we kind of get that since our environment's always changing, you know, the temperature in the rooms change, temperature outside changes, your mental state of consciousness, can that affect your internal environment? And it's constantly changing, it really can. So what we have that is a beautiful, beautiful thing is we have an entire system that is designed for these thousands of changes that are going on. We have this system that's designed to actually set points for all these different parameters and to set a high normal range and a low normal range that's acceptable. And these tissues that are made of cells, these tissues in the nervous system, are detecting these levels. And whenever something gets a little high, it will be detected, and a response will happen that will bring it what? Back down into the normal range. And whenever the nervous system does what? Detects that it gets low, what will the nervous system do? It will send a reaction that will cause it to come back up. And then it will detect this stimulus is high, so it will do something to bring it back down. Are we good with that? Very good. All right. So what's not good is that this pen isn't writing exactly where I'm touching, but that's okay, as long as y'all can see what I'm writing. So we have an entire nervous system that is setting our set points, setting the set points, and making sure that we are vacillating around those set points. Fair enough? And if we can stay in this, we're in a state of balance, or we're in a state of health, or we're in a state of homeostasis. Fair enough? Right. Almost everything that goes on inside of us uses this type of feedback reaction to keep you in a state of health. Almost everything. Okay? So this is the main way. This, I want you all to know, is called negative feedback. And this is the way we mostly maintain a state of balance. It's called negative feedback because whatever stimulus is detected, whether it's high or low, it's going to be negated. Do you get what I mean? If it's high, it's going to be negated. If it's low, it's going to be negated. It's going to be returned, right? So it's called what? Negative feedback. All right, so good. I want to give you an example, all right? So, I mean, there's tons of things we could talk about, and we will as we go along in our study of BNP. I could talk about blood calcium levels, magnesium, phosphate. I could talk about temperature, just everything, so many things. But I'm going to give you one called blood glucose. What do people say when their blood glucose levels are too high? What do they say they have? Well, okay, some of them say, no, they don't. They say they have sugar. You know that. Oh, they say they have sugar. Yeah, well, anyway, blood glucose levels. Blood glucose levels should be maintained, and different hospitals are going to have different level things, but you know, roughly 70 milligrams per deciliter to 110, let's say. All right, and you want to kind of stay in that range for blood glucose levels. And I'm going to tell you why we are so glad our nervous system is detecting this. Because here's the thing about glucose. We love glucose. Glucose is the main, best source of energy for our cells. It is the main, best source of energy for our cells. It gets a bad name, but it is. We have to have it because if our cells don't have it, our cells don't have energy. And if they don't have energy, they can't do what? Work. Right? So our cells need glucose. So if our glucose levels are getting too low, the first cells that are going to be affected are, guess which ones? The nervous system cells. They're running the show, but they're the most susceptible to any changes outside of homeostasis. This is why when you see things, sometimes over the counter, sometimes legal, sometimes illegal, sometimes prescribed, that can depress or excite the nervous systems, you should think carefully. Because the nervous system is controlling everything through this feedback. Glucose is wonderful. We have got to have it because our cells are functioning at optimal level as long as we're in here. If it gets too low, the cells can't get the energy they need to do what they need to do. If it gets too low, a person can go into a coma. It looks a whole lot like sleep. So when somebody says, oh, I don't think I need to do that check because they're resting so carefully. No, they're not. They might be in a coma. Go back and get the glucose levels. Because what comes after the coma? Death. Too low is bad. Well, what about too high? Because glucose is a good thing. You have more energy, right? No, because glucose too hot is neurotoxic. What does that mean? It means it's poison to the nervous tissue. So people who keep chronically high glucose levels are damaging their nervous tissues. How many of you know diabetics with diabetes mellitus that say, I just don't feel good unless my sugar's around 200? Do you know people? You do. She's laughing because she's heard it. So, I feel a little shaky if and by the way, they do feel shaky because they've got their bodies have kind of gone to that. But if they have levels that are staying too high for too long, they're slowly poisoning, damaging their nervous system. And this is why neuropathies go along with diabetes mellitus. Okay, so let's get back to this stuff. But usually, we can kind of try to stay in this. And so how does that happen? As blood glucose levels start to go up, it's not a big deal because what do we have detecting it? Nervous system. The nervous system is the reason it's so amazing is that it's the great communicator. Nervous system cells can communicate with other nerve cells, but they can communicate with glands and muscles and all kinds of different cells. And in this case, they communicate with an endocrine. Do y'all like how I'm writing over all this? An endocrine gland called the pancreas. The pancreas is an amazing endocrine and exocrine gland. And the pancreas, are y'all good? Everybody's good? The pancreas is going to release a hormone. So the pancreas is a gland that the cells, very specialized cells in the pancreas, will release a hormone called what? Insulin. And insulin, guess what insulin will do to this glucose that is getting too high? Insulin, because we are a cell. This classroom is a cell, okay, so we're a cell, but pretend that Julie's glucose and we're outside in the hallway. Y'all pretend we're out there. I'm insulin. I'm going to escort Julie. I'm going to escort her into the cell. Glucose by itself can't get into the cells to be used. It needs an escort. So as long as there's insulin out there, it's escorting glucose into the cells. And once it's going into the cells, what is it coming out of? What's it doing in the bloodstream? If it's going into your cells, inside your cells, where did it come from? The blood, right? So now the blood levels are starting to do what? Drop. Insulin doesn't just escort glucose out of insulin. Insulin also causes glucose molecules to get together. Insulin does this out in the bloodstream, and it causes these, it's bossy. And so it's causing them to get together. And then you all, as a big molecule, y'all will go to the liver and to muscles and be stored as a substance called glycogen. So insulin is decreasing blood glucose levels by escorting some glucose right into the cells to be used right then. But also making something called glycogen. Y'all write that down, glycogen. Glycogen, that's a C. Glycogen. And what did I tell you that big molecule of glycogen was going to go? Where were they going to go? To the liver and to muscles. And by going there, did they get out of the bloodstream? Yeah, so what's happening to blood glucose levels? They're going down. And now it's been an hour or so after you ate, and now your blood glucose levels are what? Not too low, but what? Normal low. But they're getting low, right? And that's okay, because what detects it? And what's the nervous system going to do? Send a signal to which gland? Oh, good. Stop. Pancreas. And what's the pancreas going to make? No. It can't make insulin. Not now. Not right here. Because if it made insulin, you keep going down and you die. Students tell me I say that all the time. And that would kill you. That is true. That would kill you. Okay. And this is how people in the hospital die from insulin shock. They get insulin. And guess who gave it to them? Nurses aren't only primary care providers, they're executioners too. And I mean that in the nicest of ways. I mean, I really do mean that in the nicest of ways, because usually the execution is awesome. But if it's to have given insulin right here, this person's going to die. They're going to go into insulin shock and die. And that happens. More diabetics die from insulin shock than they do high glucose. Insulin's a serious drug. Don't you ever give it to somebody unless you know what their glucose levels are. And don't ever give it to somebody unless you know what it does. What does it do? Drops blood glucose levels. So no, it's not insulin that it's going to be releasing. It's a different type of cells in the pancreas. And these cells are going to release something called glucagon. Glucagon. It's a hormone. This is a hormone, and this is a hormone. So what will glucagon do as a hormone? I saw what insulin did. I was the insulin. I escorted some into the cells, and I created glycogen to go to muscles and liver. Why did I send glycogen to the muscles and the liver? To use later. So guess what glucagon targets? It targets the glycogen, and it breaks it down. And as it's breaking it down, what are those little break down, guys? Hook together, glycogen. Where's my glycogen? Come on, Megan. Where's my glycogen? Now glucagon is breaking you down, and now what do we have back in the bloodstream? Glucose. Do y'all see that? And now glucose is coming back up. You do this all the time. Your nervous system is constantly figuring out what you need, whether you need a release of insulin or whether you need a release of glucagon. If you got a patient that has a really low blood glucose levels acting kind of a little bit drunk to you, why are they acting drunk? Because what did I tell you needs glucose most? Especially which tissues? That's why people who are in hypoglycemic situations can seem like they're drunk to you, because it depresses the nervous system. What did I tell you about depressing the nervous system? Don't do it, right? Because it's controlling everything else, right? But if they're not in a coma yet, and aren't going to choke to death, then you're going to either give them glucagon to try to get that blood glucose back up, or you're going to give them orange juice or sugar or something. You're going to, as long as you're not choking them, you're going to give them something to bring that glucose back up because you've got a short period of time. All right? Do you have any questions for me? This is like a classic negative feedback example, and I do want you all to know it. Okay? All right, good. And this will also be like just a preview of what your endocrine system chapter will be like, because for most hormones, we're going to go through this for the hormones study. Of course, that's not until AMP2. Okay? So like I said, I don't test you on anything we didn't do yet. So just take this a mouthful at a time, all right? All right, so is there any questions about this? Let's look at this negative feedback, though, and just ignore the pancreas and glucose and think about it being cold. It is your nervous system that's detecting and keeping you thermoregulated. So when you are sensing that the nervous system sensing that your core, your organs are getting too hot, they got to do something to cool down. So what you're going to end up doing is these peripheral vessels are going to dilate. Blood is going to come to the surface. Water will move into the tissue spaces. You'll start to sweat, and that's going to hopefully cool you down. Hopefully you're also sensing that you're hot, so you might start taking off clothes or getting under the tree, right? So you're doing things like that to cool down. Now, once you cool down too much, then those vessels have to constrict. Blood is diverted back to keep the organs, the core organs, where they need to be. You're probably shivering, because anytime you shiver and muscles contract, you give off heat, right? So you're giving off heat, and hopefully you're also conscious of it, so you're putting on what? Clothes, right? Or something. So this happens. This is happening at any given millisecond for thousands of things. Isn't your nervous system amazing? Really? All right. All right. So great, guys. And I've done homeostasis. Now, there's one thing. Let's talk about thermoregulation. How you know it's like a house thermostat. Your house doesn't stay at just one thing. It's going up and down. It's vacillating, isn't it? Same thing with negative feedback. Now, what I do need for you to know is that it's not the only feedback. There is something called positive feedback. And in positive feedback, maybe it would make sense to you that the stimulus that gets detected isn't going to be reversed. Stimulus reversed, stimulus reversed. The stimulus that's detected will be enhanced. This is rare that the body uses positive feedback, but sometimes it's needed. And the body can only stay in positive feedback for very short periods of time, because if not, it's going to throw everything else off. But there are a few things that the body uses positive feedback for. One of them is childbirth. So if y'all look at this muscular sac called the uterus, you see that muscular sac called the uterus where the fetus is? And you can see part of that muscular sac is extending into the vaginal canal. This is called the neck of the uterus. Neck, another word for neck is cervix. So this is the cervix of the neck of the uterus. It's extending here. What happens is, in this later part of the third trimester, is that hopefully head down position, because that's the right position, and losing room here. Some gotta give, right? So a lot of pressure will be put on these cells of the cervix. And as the internal, it's called the internal os, as these cells get pressure and stretched, and as the fetus starts to get stressed, the fetus will secrete products too that initiate this. This fetus is going to send cortisol, but also the cervix is going to send to our brain, so that we get something called oxytocin released from the brain. It's actually from the posterior pituitary, but hypothalamus, posterior pituitary. Oxytocin floods the bloodstream, hits the muscle of this uterus, and this muscle contracts. When this muscle contracts, the head pushes harder on these thinning, and more oxytocin, and more and more and more, until this fetus is expelled. If you thought you actually pushed that fetus out, you were delusional. It took the oxytocin contracting that. How many of you have had natural childbirth? You know that you couldn't have pushed that fetus out. That was not going to happen. That uterus has to contract at just an almost crazy. Like the contraction's crazy, aren't they? So anyway, in a good way, crazy. So that oxytocin is contracting for childbirth, and it's enhanced. Did y'all notice how those contractions came quicker and got harder until what happened? Until not only the fetus was out, but the placenta is delivered, and then oxytocin staying around because that uterus gets back to pre-gravid size and shape within just a couple weeks. I wouldn't recommend doing anything soon enough, okay? But I'm just saying, it gets fat. And it gets fat because of oxytocin, right? So this is a positive feedback. How many of you have had the letdown response for milk? You know that babies can't suck milk out of your breast. Poor, bless their little hearts. They don't have those kinds of muscles. But what they can do is they can suck enough that your body gets the signal for oxytocin, same oxytocin, same hormone, to initiate those contractions of your breast. My best friend used to call them orgasms of the breast. So anyway, and they are a little bit like that. So anyway, by the way, orgasms, guess what kind of feedback they are? Real orgasms. It's going to be positive feedback. And you might think it would be a good idea to stay there for a long time, but no. That gets over after that. So, okay, I'm just saying. Another thing are blood clots. Blood clots are wonderful. They keep you from doing what? Bleeding out. But if you have a vessel that has had a breach in the vessel, and you better block that breach, right? And you need to, you're going to go into a positive feedback loop, and we'll talk about this when we get to hematology, how it happens. And a platelet plug will form, and then a clot will form, but then it needs to stop. Because if it didn't stop, what would it end up blocking? The entire vessel. And any tissue past that point that was relying on, and all tissues rely on blood supply, any tissues relying, the tissues would start to die. So positive feedbacks are great up to a point, and there are a few examples. The one I gave you are examples of positive feedback, but it's kind of rare that positive feedback is used in the body. Mostly we use what? Negative feedback. All right. So look, guys, I do want to talk to you just briefly about this and how much stuff. And I'll give you a quick break. And then the last thing I have, I think we'll be done about 12:15. That gives anybody an idea of what to do today. But I want to tell you something about fever. Is fever a good thing or a bad thing? Okay. A fever, changing your body's thermostat is the brain, the hypothalamus. It creates your thermostat, keeps you at regulated. A fever is a good thing. The body recognizes when tissues have been insulted, whether they've been insulted because of injury or insulted because of viral illnesses or bacterial illnesses or whatever. The body's immune system recognizes that by raising the thermostat, the body's metabolism will go up. And as the cell's metabolism have gotten permission to increase their work, what can happen faster? Healing, right? Repair. All of that's going to happen faster, right? Are we with me on this? Also, the raising of the thermostat might be just enough to discourage replication of infectious processes, infectious organisms. They might like your body temperature, 37 degrees Celsius, but they may not like a slight higher. So it can limit infectious processes, and at the same time help with healing and repair. So is fever a good thing or a bad thing? It's a good thing up to a point. And it is true up to a point. The thing about us and y'all probably don't appreciate the way, I'm doing some things just dramatically, right? Kind of, don't judge me. Okay, look. But seriously, in our society, we can't stand any inconvenience. That's why we have all this over-the-counter drugs that should not be. We have antipyretics that are people changing their thermostats. We have anti-inflammatories, and we have so much stuff that are really serious chemicals. And the thing is, we don't want to be inconvenienced. We don't want to have a stuffy nose. We don't want to have a temperature. We don't want to have an knee ache. We don't want to have any aches. But all of those things are protected. They're protected up to a point. Now, you can have too much inflammation and your fever can go too high, and then you need some support. You really do. What happens, though, typically, is that when the body resets its thermostat, you will see, if you give it enough time, what almost always happens is that you'll be now vacillating around a new set point. But you are vacillating around that new set point. And if you were to see that, not that anybody lets that happen, you should leave it alone. The problem comes in when you don't see the new stadium being reached, and what you see is a continuing climb. If you see a continuing climb, you've got to stop it. You've got to take an antipyretic, because you can get into a positive feedback loop, and because your temperature's so high, your cell's own proteins are starting to denature. And when the cell gets a signal that they're denaturing, the cell's having to work harder to make the proteins. And every chemical reaction the cell has to do puts off what? Heat. Then you're breaking more proteins, then you're having to make more, and you're giving off more heat. Do you get what I'm saying? So if you don't see the new stadium being reached, the new set point being vacillated around, you need to stop the climb. Because it could get like this, and it's rare that it's like, you ever seen anybody like that? No. I've only seen a couple people die in the ER from this, and that's ridiculous. They were like 108, 109, and couldn't get them back. But they were already gone really before they came in. So you don't want somebody to get too hot. Babies can withstand a lot higher temperature than adults can. And I don't mean that just because babies don't want as much as adults. I mean that because physiologically, adults really can't take the kind of heat so anyway, but if you were to see that new stadium, you really wouldn't want to do anything with it. All right, now, just because I'm going to stop right here, okay? Let's take a quick break and then come back, and then I have about 30 minutes or so of a lab 1. I call it lab 1. And so how much time do y'all want? 10 minutes, 15? Do y'all want longer than that? Are you hungry? Okay, can we say like quarter till? That's 12 minutes. We're going to start lab at quarter till. Please be here at that time, okay?
Come back in here.
Yes, just come back in here. Yes, that's a great question.